Let's start working through our example numerically now. So let's ask, what is the charge on the surface of a 20 centimeter radius Van de Graaff generator if the charge is 50,000 volts? So something we know about spherical charges is that a sphere of charge is like a point charge when you're outside of it. That's the same as the electric field. When you're outside of a spherical charge, the electric field looks just like that of a point charge. So that means that anytime we're outside our Van de Graaff generator or right at the surface, we can use the expression V equals KQ over R, where R is the distance to the center, Q is the charge, and K is Coulomb's constant. Okay, so if V equals KQ over R, we can find Q is going to be V times R over K. V is our 50,000 volts. R is the radius, 0.20 meters. K is our Coulomb's constant, 8.99 times 10 to the 9 coulombs meters squared. Newtons times meters squared over coulombs squared. That gives us a charge of 1.11 microcoulombs, or times 10 to the minus 6 coulombs. So that's the net amount of charge on the surface of a Van de Graaff. To me, this gives an indication of how big a coulomb is. 50,000 volts is a lot of potential, but a microcoulomb doesn't feel like very big charge. So I guess what this can show us is that a microcoulomb is actually a great deal of charge, and a coulomb is a very large amount of charge. Okay, next task. Let's draw the equipotential lines and the electric field lines around a Van de Graaff generator. So let's do the electric field lines first. It's a positive charge, so the electric field lines go straight out everywhere. And they'll go out evenly in all directions. So there are our electric field lines. For our equipotential lines, let's make sure we know what we're doing there. So if V is equal to KQ over R, and an equipotential line is a line with constant potential, then to get constant potential we have to have constant R. So equipotential lines, they have constant V. Therefore, in this geometry, they also have constant R. So a line with a constant radius would be a sphere. So our equipotential lines are actually going to be surfaces, and they're going to be spherical because they all have a constant radius. The other way we do equipotential lines is that they're all evenly spaced in potential. So I'm going to find distances, radius of spheres, where the potentials go down by 1,000 volts. I'll start at 50,000 because that's going to be right at the surface. Then I'll go down 10,000 volts each time. So if V is KQ over R, then R is equal to KQ over V. Q I know because we calculated it up above. So if my V is 50,000 volts, my distance is 20 centimeters. I already knew that part. So my first equipotential line will be right on the surface of our Van de Graaff. And that's a potential of 50,000 volts. Normally you should label your equipotential lines. That shouldn't be a surprise. We know that the surfaces of conductors are all equipotentials if they're at electrostatic equilibrium. That's one of the properties of a conductor. Okay, my next equipotential line will be at 40,000 volts. So I'll do KQ over 40,000 volts, and I get a distance of 25 centimeters. So that one's going to be out a little further. It's hard to draw my circle perfectly, but I'll give it a shot. So this one is 40,000 volts. My next one is going to be at 30,000 volts. That happens if R equals 33 centimeters. So we'll notice now that the lines are starting to space out a bit. They're pretty tight and close to the surface, but they spread as we get out further. That makes sense because the equipotential lines are close together where the field is strong, that's in next to the surface, and they're spread out where the field is weak, that's further out from the surface. Okay, there's my 30,000 volt line. My next one at 20,000 volts has a radius of 50 centimeters. Draw that one next. So that's out a bit further. It's hard to get the circles really good. 20,000 volts. And then my last one is my 10,000 volt line. That happens at exactly 1 meter. And of course, if you wanted to plot this, you could go onto the PhET simulation and see what it looks like there. It should match what you find here.